Hi everyone, welcome back to my channel. Today I am going to solve Nuclear Chemistry CSIR NET previous year questions. If you have not subscribed to my channel, please subscribe the channel and like and share the video. Let's move to the question. This question is asked in CSIR NET June 2016 and the question is on two sequential electrons capture BA56131 will give. Here option is given as xenon 131 and 54, cerium 131 and 56, xenon 130 and 54, cerium 130 and 56. Let's see the solution. Here the concept used is electron capture. In electron capture, a proton converts into neutron. That proton plus electron gives rise to neutron. In this, atomic number Z decreases by 1 and mass number A remains same. Now we'll see the solution. Here initial nucleus is given as beryllium 56 and 131. In this beryllium, in this beryllium, Z is equal to 56 and A is equal to 131. Here they asked two subsequent two electron capture. After first electron capture, Z is equal to 50, Z is reduced to 56 to 55. So A is same, that will remain as 131. And after second electron capture, the 55 will be reduced to 54 and A will remain same. So here the final answer will be Z is equal to 54 and A is equal to 131. So here element xenon will be xenon 134. Here the element is xenon 131. So the correct option A. Xenon 131 and 54. Option 1 is the correct one. So we'll see the second question. On continuous exposure of 10B sample to a slow neutron flux of 10 to the power 16 meter square per second, it is observed that 3% of the sample disappears in 3 into 10 to the power 7 second due to neutron capture. Calculate the neutron capture cross-section sigma in barns. This has asked in CSIR NET June 2016. Here option given as 100 bars, 500 bars, 1000 bars and 3000 bars. You see the solution. Here the concept used is exponential decay under neutron flux. Here, when a nucleus is exposed to neutron flux, the number of nuclei decreases as n is equal to n naught into e to the power minus sigma phi t. A ratio form is given as n by n naught is equal to e to the power minus sigma phi t. Here n naught is initial number of nuclei, n is equal to number of nuclei after time t, sigma is equal to cross section, phi is equal to neutron flux and t is time. See the solution. Here given what has given flux phi is equal to 10 to the power 16 meter square 16 per meter square per second and time t is given as 3 into 10 to the power 7 second. 3% disappears means 97% remains. So n by n naught is equal to 97 divided by 100 is equal to 0.97. Now we'll solve in stepwise. In step 1, apply formula. Formula is n by n naught is equal to e to the power minus sigma phi t. So n by n naught is 0.97. So 0.97 is equal to e to the power minus sigma phi t. Take ln. Ln of 0.97 is equal to minus sigma phi t. Now, step 2, use approximation. Ln 0.97 is equal to minus 0.03. So, here minus cancels each other. Sigma phi t is equal to 0.03. In step 3, we have to substitute values. Sigma into 10 to the power 16 into 3 into 10 to the power 7 is equal to 0.03. So sigma into 3 into 10 to the power 23 is equal to 0.03. Sigma is equal to 0.03 divided by 3 into 10 to the power 23, and sigma we will get as 10 to the power minus 25 meter square. In step 4, we have to convert to barns. Here 1 barn is equal to 10 to the power minus 28 meter square. Sigma is equal to 10 to the power minus 25 divided by 10 to the power minus 28. So you will get 10 to the power 3. That means 1000 barns. So final answer sigma is equal to 1000 barns is barns. So option 1 is the correct one. Let's move to the third question. This was asked in December 2016. The question is saturation factor in neutron activation analysis is A is equal to induced radioactivity, phi is equal to neutron flux, sigma is equal to effective nuclear cross-section, and n is equal to number of target atoms, lambda is equal to decay constant. And option is given as A divided by phi sigma n, and option 2 is phi sigma n A divided by lambda, and 3 is sigma divided by A phi sigma n, and fourth is pi sigma n divided by A. Let's see the solution. Here the concept used is neutron activation analysis. The activity produced during irradiation is A is equal to pi sigma n divided by lambda into 1 into e to the power minus lambda t. At saturation T to infinity, A infinity is equal to phi sigma n divided by lambda. Saturation factor is equal to A by A infinity is equal to A by phi sigma n divided by lambda. Compare with options. A divided by phi sigma n divided by lambda. This exactly matches the definition of saturation factor. So option 1. So option 1, A divided by phi sigma n is the correct one. Now let's move to the fourth question. This is asked in CSIR NET June 2017. Consider the following statements for fission of uranium-235 with thermal neutrons. Option A is given as the percent of nuclei undergoing unsymmetrical fission is maximum, and B is in each fission one thermal neutron is produced, and C is magnitude of energy released per fission is of the order 200 mega electron volt. Correct statements are option A. One is A and B, A and C, B and C, and C only. Let's see the solution. Here given fission of uranium 235 with thermal neutrons. Statement A is given as the percent of nuclei undergoing unsymmetrical fission is maximum. Actually, this is the correct one because in uranium 235 fission, products are not equal in size. Typically, one fragment is equal to 95 and another is equal to 130. So, asymmetrical fission dominates. So, statement A is correct. See the statement B. Statement B, in each fission, one thermal neutron is produced. Actually, this is the incorrect one because fission produces 2 to 3 fast neutrons, not thermal. These neutrons are high energy initially. They become thermal only after moderation. So, not one neutron, not thermal neutron. Thus, that statement B is incorrect. Let's see the statement C. Magnitude of energy released per fission is of the order 200 mega electron volt. This is the correct one. The standard value of energy is 200 mega electron volt. So the option C is correct. So final answer A and C are correct and option 2 is the correct one here. I hope you understood this video. In next video I will solve some more nuclear chemistry previous year questions and follow for more chemistry content. Thank you. Have a good day.